NASA has a much more ambitious lunar program called Artemis.
We're excited to be the first crew in over 50 years to go out to the moon and back.
With the rise of private space companies and renewed international competition, the race to explore the final frontier is heating up. At the forefront of this endeavor stands NASA, driven by the unwavering ambition to conquer deep space. This journey begins with the invaluable experience gained from the International Space Station. Building upon this foundation, NASA's ambitious Artemis program charts a course toward the moon. Still, the journey from the Apollo missions to the Artemis 1 flight isn't easy. Let's look at how NASA plans to change space travel as we know it. Orbiting around the Earth at 17,500 miles per hour, the International Space Station is a marvel of human ingenuity and international collaboration. The ISS is a massive artificial structure circling Earth, the result of collaboration between 5 space agencies: NASA of the US, Roscosmos of Russia, JAXA of Japan, ESA of Europe, and CSA of Canada. It holds the title of the largest space station ever built. The ISS program emerged from merging 2 earlier proposals, the American Space Station Freedom and the Soviet Mir-2 station. The first module launched in 1998, with astronauts arriving for a long-term stay in November 2000. This marked the beginning of the most extended, uninterrupted human presence in space, exceeding 23 years as of March 2024. The station has hosted 279 people from 22 countries so far. But beyond its awe-inspiring presence, the ISS is a major chess piece in NASA's ambitious Artemis program, which plans to build a sustainable human presence on the moons. Establishing human presence on the moon is a big goal. How does NASA plan to achieve this? The Artemis mission. Man's first landing on the moon in 1969 marked a pivotal historical moment. The Apollo missions, a series of audacious endeavors by NASA, culminated in Neil Armstrong's iconic footprint on the lunar surface. The Apollo program was a race against time, fueled by the Cold War rivalry with the Soviet Union. It demanded groundbreaking rocketry, spacecraft design, and life support systems advancements. However, after Apollo 17 in 1972, the silence of the moon descended once more. Now, over half a century later, NASA's Artemis program signifies a thrilling resurgence of lunar exploration, building upon the legacy of Apollo. The Artemis program, which derives its name from the goddess of the moon, signifies a bold new chapter in lunar exploration. Unlike Apollo, Artemis is not solely focused on achieving a singular first. It aims to establish a sustainable human presence on the moon.
The goal for this decade is out of landing a man on the moon and returning him safely to the Earth.
The Artemis program relies on a complex and powerful set of technological marvels to achieve this project. At the heart of this endeavor lies the Space Launch System. This colossal machine, capable of generating over 8.8 million pounds of thrust, will propel the Orion spacecraft, carrying astronauts on their lunar journey. The Orion spacecraft is a marvel of human engineering, designed to provide safe and comfortable transportation for astronauts not just to the moon, but potentially to even farther destinations. Another critical component of Artemis is the Lunar Gateway, a mini space station that will move around the moon. This gateway will serve as a crucial staging point for future lunar missions. Astronauts traveling from Earth can dock with the gateway and then transfer to lunar landers for descent to the surface. The gateway will also serve as a research platform, enabling astronauts to conduct scientific experiments in lunar orbit. While it appears to be based on the Apollo-era Saturn V rocket, it has more going on. The system is a heavy-lift machine capable of launching payloads weighing more than 100 tons into lunar orbit or beyond. Artemis 1, launched in November 2022, it marked the program's first mission. It was an uncrewed test flight of the Orion spacecraft and the Space Launch System. Orion, designed to carry astronauts further into space than ever, successfully orbited the moon, venturing thousands of kilometers beyond. Although Artemis was superior to Apollo, it could not reach the moon as quickly as Apollo. The question is, why would an invention made 50 years ago be faster than modern NASA technology? Artemis 1 challenge. Unlike the Apollo missions that took a seemingly direct path to the moon, Artemis 1 embarked on a more complex, looping trajectory. This difference raises a crucial question: why doesn't a mission to our closest celestial neighbor follow a straight line? The answer lies in the immense energy required to escape Earth's gravity and reach lunar orbit, a challenge tackled differently by Artemis 1 due to the limitations of its Orion capsule. At the heart of this challenge lies a concept called delta V, which measures the velocity change needed for a spacecraft to complete its journey. Getting to the moon requires a significant delta V, surprisingly even more than reaching Mars. This might seem counterintuitive since the moon is much closer. The reason lies in the Earth's gravitational pull, which is strongest closer to the planet. Escaping this pull demands a significant amount of energy. Hence, the high delta V is needed for lunar missions. The goals of Artemis 1 also contribute to its unique trajectory. Unlike the Apollo missions that aim to land humans on the moon, Artemis 1 focuses solely on testing the Orion capsule. This difference in aspirations translates into the capabilities of the spacecraft. The Apollo missions utilized the Saturn V rocket, a mighty behemoth that provided enough delta V for a direct, quick route with a long burn to slow down upon reaching the moon. However, like we said earlier, the Artemis 1 mission utilizes the Space Launch System rocket, which, although more potent than the Saturn V, faces limitations with its Orion capsule. Here's where the delta V concept becomes critical. While the SLS might be mighty, the Orion capsule has a lower delta V than its Apollo counterpart. This discrepancy arises from a design choice. The Orion capsule prioritizes a spacious crew module for future human missions, at the expense of a smaller service module, with less fuel capacity and thrust. On the other hand, the Apollo missions opted for a smaller, lighter crew module in favor of a larger service module, with more fuel and engine power. This trade-off directly impacts the delta V available, resulting in a less fuel-efficient but quicker route for Apollo. With a lower delta V at its disposal, Artemis 1's Orion capsule wouldn't have enough energy for such an approach. It wouldn't have the fuel reserves to perform a direct flight and a quick lunar burn to enter orbit. This limitation is the driving force behind the mission's unusual trajectory. This challenge almost stopped the Artemis launch project, but NASA devised an ingenious strategy to help Artemis 1 navigate this hurdle and reach its lunar destination. Solution: distant retrograde orbit. NASA introduced the distant retrograde orbit (DRO) concept to battle this challenge. Despite the Orion capsule's limitations, this ingenious solution allowed Artemis 1 to achieve its lunar goals. In contrast to Apollo's near-circular lunar orbit,
actually commit us to leaving the lunar orbit and coming back towards Earth.
a DRO is a highly elliptical orbit that took the spacecraft far out beyond the moon before looping back around. While it took significantly longer days, 12 days for Artemis 1 compared to Apollo's 3 days, this extended journey offered several advantages. Firstly, the DRO leveraged the moon's gravity to its advantage. As Artemis 1 approached the moon from the opposite side of its orbit, the moon's gravity acted like a giant cosmic brake, slowing the spacecraft down significantly. This gravity assist maneuver conserved precious fuel that would otherwise have been needed for a conventional engine burn. Secondly, the DRO allowed for an extended testing period for the Orion capsule. Engineers could thoroughly test the spacecraft's systems and life support capabilities under various conditions by spending a significant amount of time in lunar orbit. This extended testing period became crucial for future Artemis missions with human crew on board. The journey doesn't end with the assistance of gravity. To achieve a stable lunar orbit, Artemis 1 still needed a final engine burn. The distant retrograde concept of Artemis 1 utilized the Oberth effect. This principle states that a spacecraft gained more velocity by burning its engines closer to a massive object like the moon due to the additional gravitational pull. Imagine two runners, one on flat ground and the other running downhill. The runner going downhill expends less energy to achieve the same speed as the runner on flat ground. Similarly, by performing its final burn near the moon at its closest approach, Artemis 1 maximized the efficiency of its fuel usage. The stronger lunar gravity provided a boost to the burn, allowing the spacecraft to gain more velocity with less fuel expenditure. While successful, Artemis 1's mission duration was limited due to the constraints of the Orion capsule's life support systems, and it was an uncrewed mission. So how does NASA intend to conquer the moon if they can't even send humans there? Let's find out. Artemis 2. To solve the issue, NASA proposed the Artemis 2 project. The Artemis program takes a giant leap forward with Artemis 2. This mission, targeted for launch no earlier than September 2025, signifies a crucial turning point. It will be the first crewed mission of the Orion spacecraft and the mighty Space Launch System rocket. Unlike its predecessor, Artemis 1, Artemis 2 will carry a crew of 4 astronauts. Their primary objective is to perform a daring lunar flyby, venturing thousands of kilometers beyond the moon without actually landing. This mission serves a multitude of purposes. Firstly, Artemis 2 will be the first time astronauts interact with Orion systems in a deep space environment. This critical test will evaluate crew comfort, life support capabilities, and their ability to operate the spacecraft on a multi-day mission. Secondly, the mission will push Orion's limits, showcasing its ability to sustain life for extended periods beyond low Earth orbit. This includes evaluating the spacecraft's navigation, communication, and environmental control systems under deep space conditions. Most importantly, the Artemis 2 will test the planned mission profile for future lunar missions. The chosen trajectory utilizes a free return path, meaning the moon's gravity slingshots Orion back toward Earth in case of engine malfunctions near the moon, ensuring a safe return journey. The awe-inspiring liftoff will occur from Launch Complex 39B at Kennedy Space Center. The colossal SLS rocket will propel the Orion capsule on its journey towards the moon. Following launch, Orion will spend a brief period in Earth orbit for final checks and maneuvers before departing for the lunar frontier. Crucial system checks ensure a safe and successful journey beyond Earth's atmosphere. This is the heart of the mission. Orion will approach the moon, venturing thousands of kilometers beyond it. This close encounter provides valuable data on lunar influence on the spacecraft's trajectory and offers astronauts a breathtaking lunar vista. Utilizing the moon's gravity for a slingshot effect, Orion will be propelled back toward Earth on its free return trajectory. This path ensures a safe return even in case of engine malfunctions near the moon. Re-entering Earth's atmosphere at high speeds, Orion's heat shield will protect the crew during the fiery descent. The mission culminates with a splashdown in the Pacific Ocean, where recovery teams will await the returning astronauts. Establishing a lunar base, Artemis 3. Artemis 2 paves the way for Artemis 3 and beyond, aiming to establish a sustainable human presence on the moon.
From seeing entire moon colonies being built using this approach.
The moon holds a treasure trove of scientific knowledge waiting to be unlocked. A permanent lunar base will allow scientists to conduct extensive research in various fields. Geologists can study lunar rock formations, providing insights into the moon's formation and history. These studies might shed light on our solar system's early stages and potentially even planets' formation. Furthermore, the moon's polar ice caps, rich in water ice, can uncover clues about the presence of past water on the lunar surface and possibly the existence of past or even present biological activity. While a concrete timeline for a lunar base hasn't been established, NASA is actively exploring potential designs and technology needs. Here's a glimpse into some existing concepts. NASA plans to build an Artemis-based camp, envisioned as a starting point. This initial lunar outpost would likely be a small inflatable habitat utilizing resources delivered by Artemis missions. Utilizing lunar regolith for 3D printing could revolutionize lunar base construction, reducing reliance on Earth-launched materials. Additionally, extracting water ice from lunar polar craters could provide a sustainable source of water for the base, enabling life support systems and potentially propellant production. NASA is projecting around $93 billion for this Artemis program. With around $4.2 billion per launch, do you think this is sustainable? Will NASA be able to pull this one off? Feel free to let us know your thoughts in the comment below. Don't forget to like and subscribe to our channel so as not to miss out on future updates.